Looks like everybody's settling in a good mood. Or you just got out of bed and you don't have a mood yet, you don't know. I've been up for a while, I'm in a good mood. Let's get going. So, we've been working on real symmetric matrices. This is our entry point. This is our entry point into starting to be able to understand the difference between linearly independent and numerically linearly independent. See, the problem with abstract linear algebra is something is either invertible or it's not. It's either independent or it's not. There's no gray zone. Engineers, we're always in the gray zone, okay? We want to be able to quantify how independent are they, how close to being a singular matrix is it, things like that. So these real symmetric matrices are our first entry point into understanding some of the numerics of the calculations that we end up having to do as roboticists, as control engineers, etc. Okay, so the first thing we showed is if a matrix is real and symmetric, its eigenvalues are real, and hence we can always take the eigenvectors to be real. And then we showed if the eigenvalues are distinct, then the corresponding eigenvectors are orthogonal. And then in the homework that you will have after the break, no homework due during the break, the homework after the break, you will treat the general case when there are repeated eigenvalues. So you'll have a, okay. Question? Break, got everybody excited?
What do you mean after the break? Homework to go on Thursday.
We have class on Thursday,
Right.
yes, but we're not going to make you do homework on Monday and Tuesday.
But you can't stop us from doing homework.
No, I will post it, but you won't be due on Thursday of next week.
Okay.
Does that make sense? Okay, I'm gonna make 2 homeworks due next week, okay? And if anybody complains, they go talk to Nosa. He has to do it. Okay, now that we got that excitement out of the way, homework 6 will treat the general case of when you have real symmetric matrices. You'll show that even if the eigenvalues are distinct, you can build a basis for the eigenvectors that is orthogonal. So you'll get the general case. So once we had this, we said, we just looked at our case of similar matrices. We had the idea of an orthogonal matrix. It's a matrix whose columns are orthonormal. Okay, so there's an incompatibility between the notions in abstract inner product spaces of vectors being orthogonal and unit length, and the definition of an orthogonal matrix, okay? Those two communities did not get their vocabulary coordinated perfectly. So you just have to remember that a matrix is orthogonal if Q transpose times Q is the identity. And since the ij element of this matrix is the ith column of Q inner product with the jth column of Q, this really means they are orthonormal, okay? And so when it's orthonormal, its inverse is trivial. It's just a transpose. Instead of having M inverse A times M, we have Q transpose A times Q equals a diagonal matrix. So A is similar to a diagonal matrix through an orthogonal transformation. So it's just a change of basis. And then we also noted that orthogonal matrices preserve the lengths of vectors. So it's not taking a short thing and making it into a long thing or anything like that. It's just rotating the vectors is all it's doing. Questions? Okay, orthogonal matrices, we like them. Symmetric matrices have wonderful properties. Okay, then we started looking at essentially what we're getting ready to do here is build a more general inner product than just X transpose X. We're going to put a weighting matrix in here. So we looked at these quadratic forms for M, not necessarily symmetric, and we decomposed it into a symmetric part and a skew symmetric part. And we noticed that X transpose times skew symmetric times X is identically 0. And so this only depends on the symmetric part of M. Hence, whenever we write down a quadratic form, we never take anything except symmetric matrices. It is not more general to put in a general matrix because it just replace it with the matrix plus its transpose over 2. So you can always assume this is symmetric. Always symmetric, okay? Based upon that, we made a definition that a symmetric matrix is positive definite if X not equals to 0 means X transpose PX is not equal to 0. It's actually, positive. Why is this interesting? If this is the inner product of two vectors, this is saying the length of the vector is positive when the vector is not equal to 0. Okay? This will be the norm squared of the vector when you use the inner product as X transpose P times Y. So we will use that inner product. So it's getting us a more general set of inner products on Rn than just X transpose Y, which is the case P equals identity. Okay, so these matrices that are positive definite, I had set you up earlier in the term in your homework to study them as an exercise in Lagrange multipliers, and you actually got bounds essentially of the type X transpose PX is lower bounded by the smallest eigenvalue of P. Remember, P is symmetric, so its eigenvalues are real, and so a minimum exists. It all makes sense, okay? There's not a minimum of complex numbers. The smallest eigenvalue of P times X transpose X is a lower bound for X transpose PX, and the upper bound is the maximum eigenvalue of P, X transpose X. So that's true for all symmetric matrices, and hence, if P is going to be positive definite, we need the smallest eigenvalue as positive. And that's necessary and sufficient because these bounds are tight. A bound is tight if there exists an X for which this is an equality. And if you take X equal to an eigenvector corresponding to this eigenvalue, then this is equal right here. And if you take X equal to the an eigenvector corresponding to the maximum eigenvalue, then this is an equality here too. Okay, so these bounds are, one says they're tight because there's special choices of X where it's actually equal. You can't get any tighter than that. Okay, so then P is positive definite if and only if the smallest eigenvalue is positive. One also says all of the eigenvalues are positive. That's the same thing because there's only a finite number of eigenvalues of an n by n matrix. Okay, so theorem, positive definite boils down to checking eigenvalues. Okay, so that's not a very, it's an important result. This bound is very nice, but calculating eigenvalues for large matrices is extremely expensive. It's n cubed in the size of the matrix. So if your matrix is 5 by 5, no big deal. If your matrix is 100 by 100, it's a really, really, really slow process to calculate eigenvalues. So we're going to develop today a better way to check positive definite. Now, I don't know if I did such a great job with this example that we had on Tuesday of just giving an example of a matrix where, hey, its determinant is 1, so it's invertible. It's beautiful, okay? So I went ahead and multiplied out A transpose A. I would not try to copy it down right now. Just make a note in your notes to leave a page and grab this. But remember, we have this result that the rank of A and the rank of A transpose times A are the same. So in fact, the determinant of A transpose A is the determinant of A squared. This is 1, so determinant of A squared, determinant of A transpose A is 1. And yeah, that's true. It's 1 times 10,001 minus 10,000. Now, when you looked at this, you go, oh, 1, that's fantastic. When you go over here and you go, great big number minus great big number, and I'm getting a little bitty number, it doesn't take much change to make that little bitty number change sign to be 0, etc., right? It's super clear when you look at A transpose A that, oh yeah, maybe that is really close to being singular. Okay, we're here. Well, it doesn't look close to being singular. And so then this is the Q transpose lambda Q for that matrix. And so here's one eigenvalue, 10,002. And here's the other eigenvalue, minus 0.00009998, okay? Is it close to being singular? Yes, okay, okay. We don't use this really in Rob 501, but it's called a condition number when you take the maximum eigenvalue over the minimum eigenvalue here. It's 10 to the 8. Okay, if this is 50, even 100, it's like no problem, okay? But 10 to the 8, well, that causes you need really accurate measurements and computations for this not to cause amplification of error when you're doing your calculations. Okay, so you can add that. And then I just did a little bit better picture. I mean, it's still not to scale, but here's the columns of that A matrix. And so 1, 0, that's this vector here, okay? And then here's 101, kind of, okay? I don't know if that's really 1. I mean, I didn't measure it out, but I just calculated the angle and it's, 0.6 degrees, okay? So they're almost parallel, okay? Meaning almost dependent. Is this kind of making a little bit better sense? Yeah, okay. Wish I'd have done a better job on Tuesday, but there. Okay, so we'll use this for checking a little bit later in the term the numerical rank of a matrix and numerical linear independence of sets of vectors. And that'll be called the singular value decomposition. And we've done the singular value decomposition really for symmetric matrices. These are the singular values, the eigenvalues of the matrix. Okay. Make another note that I just popped in, something for you to come and look at. So, the symbol we use to say that a matrix is positive definite is we just write greater than 0. Okay, so that's the symbol. And then you also see something that's a little bit more like that, kind of a curved greater than sign. Okay, we'll leave it like that. The example is here in part to make the following point, so write that down. positive definite does not mean all of the entries are positive, okay? Just to be clear, this does not mean all of the entries of P are positive. Okay, and just to add to that, check that P equals 2, 3, 3, 2 is not positive definite. Ooh, okay. Yay, all the entries are positive, but it's still not a positive definite matrix, okay? I can find vectors where I do x transpose px and I get a negative number. So, you really have to check the eigenvalues. Later on today, we'll come back and we'll do something really simple. We'll check that this is positive. We'll check that this determinant is positive. Done. Positive definite. Okay, we'll have that result in our back pocket in about 30 minutes or so. Question? Yeah.
Yeah, so like a quick way to eliminate whether it's positive definite is maybe to check the determinant. Like in the example you gave, so
Yeah.
it's not positive definite.
Mm-hmm.
You can quickly see that the determinant is negative.
Correct. So we will have that result in about 30 minutes.
Oh.
Yeah, 30 minutes. In about 30 minutes, we'll check. This is 4 minus 9, that's negative, not positive definite, okay? We don't have that yet. Right now, you have to do all the eigenvalues. And for 2 by 2, it's not too bad, it's still not fun. And for 10 by 10, it's really not fun, etc. Oops. Hope you just won $1 million. You can define semi-definite. Positive semi-definite means x transpose px is non-negative for all x. It doesn't matter whether x is 0 or not, okay? If x is 0, it doesn't really matter, okay? It's positive semi-definite, and then using our same bound as we had before, that means that all the eigenvalues of p are non-negative. So the smallest one is greater than or equal to 0. Okay, so this example is kind of important. To do the example. And then this definition is interesting. So what's going on here? We're used to taking real numbers that are non-negative and defining a square root. Okay. So we'll say that a matrix N is a square root of a symmetric matrix P if I can take N transpose times N and get P. So it's kind of a reasonable generalization of what we mean by a root. Okay, if it was a scalar that we don't know transpose, that would be N squared equals P. Okay, so that seems pretty good. Now, if your matrix is not symmetric, you can't find a root because this product is always symmetric, okay? So just checking here, N transpose N, you transpose it, you get it back, it's always symmetric. And so the theorem that you can show, and I'll let you go through the proof on your own, if P is positive semi-definite, if and only if it has a matrix square root, okay? P is positive semi-definite if and only if it has a matrix square root. So the calculations are really just applying the fact that for symmetric matrices, we know how to write it as an orthogonal matrix transpose times a diagonal matrix times an orthogonal matrix. And the diagonal matrix, I think you know how to calculate or square root of each entry on the diagonal. So just play with that, okay? If you take that idea and run with it, you can make that work. So, okay. Do something new, the Schur complement, okay? So this is going to be how to check Schur complement theorem. Okay. It's a means for checking if a matrix is positive definite. Okay, so that's one reason this Schur complement theorem is going to be super important. The other thing is it shows up when we study conditional Gaussian random vectors. So this is just saying, yeah, we're laying the groundwork when we start doing estimation with random measurements. Okay, we're laying the groundwork for that. I'm hoping everyone in the class has seen the concept of the variance and the standard deviation of a variable. If not, start looking at it, okay? So that's for scalars, that's for random variables. When you take vector valued things that are random, the corresponding thing for a variance is called a covariance matrix. Okay. Those things are symmetric and generally positive definite too. Okay, so we'll be looking at them and we'll have a vector that consists of like state variables of our robot and measurements, and we'll be trying to estimate the top part in terms of the measurements. And when we do that, those are conditional random variables, and the Schur complement theorem will raise its ugly head unless we've already studied it and we go, oh, I recognize this term, it's just a Schur complement, I'm not afraid of it, then you'll be much happier. So this is what I'm trying to do, prepare the ground. Okay, so enough talking. What's the theorem? Theorem. Suppose A is n by n, B is m n by m, and C is m by n. C is squared, m by m. Okay? Okay, now I'm going to build a matrix out of these matrices. I'm going to put A here, B here, B transpose, and C. I'm going to suppose, and that this matrix is symmetric. Okay, so what do we need for M to be symmetric? Can you put a transpose here and see what's happening? So A has to be symmetric. B comes down here to the transpose, no problem there, and C has to be symmetric, okay? So A equals A transpose, C equals C transpose. Okay. Then T, F, A, E. You remember TFAE? The following are equivalents. We're going to say three things. Okay. The first one is that the big matrix M is positive definite. Okay. The second one is that the first block A is positive definite. And C minus B transpose A inverse B is positive definite. Okay, so we're breaking the calculation for M down into sub-blocks. A, check positive definite, and then C minus something. So this thing has a special name. Okay, this is the Schur, after the guy who did it, Schur complement of A in M. Okay. So instead of tackling the problem that M is positive definite, you can tackle the problem that A is positive definite. Once A is positive definite, we know its smallest eigenvalue is positive, and hence A is invertible, so this is well defined. Okay? This is symmetric because A is symmetric, so C minus something symmetric is symmetric, and then we can check whether it's positive definite or not. So everything's well defined. And then the other part is, instead of starting at the top, you can start at the bottom. You can check C is positive definite, and then check that A minus B C inverse B transpose is positive definite. And this is the Schur complement of C in M. Okay, so let me give you just a little bit of physical insight into this, then we'll just do the proof, and then we'll forget about the physical insight, and we'll come back to that in a couple of weeks when we could do probability and random variables. But if you kind of believe that you sort of understand what is a standard deviation and that the corresponding thing for vectors would be a covariance matrix. So if the matrix has big entries, there's lots of uncertainty, and the matrix has small entries, there's not very much uncertainty, okay? That's just the intuition. Now, if M is our covariance matrix for states stacked up, and then the next part is measurements, what this Schur Complement Theorem is telling us is that, so A is our current uncertainty in the state. I want to do it this way. This is the uncertainty down in the measurement part when we use this form of the theorem. A is the uncertainty in the states, but if I take my state variables conditioned on making a measurement, I reduce the uncertainty in A by B C inverse B transpose. Okay, I have states. We don't know exactly where they are, but we start taking measurements. We should reduce the uncertainty. Subtraction is reduction, okay? Now, if the measurements are really bad, C is huge, so its inverse is teeny tiny, and so you're subtracting off almost nothing, and you've not reduced your uncertainty very much. Yay! Now, if the measurements are very precise, there's not much deviation, so this is a really small matrix. And so its inverse is big, and I'm taking off a lot of uncertainty from A. So this theorem has lots of consequences, but for today, it's just that, hey, we have this cool property called positive definiteness, and we can break it down into looking at blocks of the matrix so the calculations are easier, okay? So we just forget about the intuition, but we'll come back to that later. Does that help, that little insight? A little bit more motivation? I shouldn't give any. This is abstract nonsense and Rob 501, remember, and we're tough and we can do it, okay? That's our real attitude. And if you tell anybody anything else, I'll deny it and I'll say that the films are fake. Okay, so whoops, I want blue. Proof. Okay, we want to show all these three things are equivalent. Okay, so we'll show A if and only if B, and skip A if and only if C, because the proof is exactly the same. Well, almost, okay? You gotta change the names to protect the innocent, because the proof is nearly identical. You just change a few symbols. Okay. Okay, so let's do A implies B first. So we have this beautiful matrix M. We assume it's positive definite. Hence, I'm going to break my variables down and call them X and Y. And if you want to think of that once again as X like a state of a robot and Y like a measurement, I'll be super happy, but I don't care. Okay? Just assume this is not the zero vector. So for all X and Y's not identically zero, we know that X, Y transpose times A, B, B transpose C times X and Y, that's a scalar, and excuse me, it's not equal to zero, it's positive. It's positive definite matrices. Okay, so that's what we know. Okay, let's go back and see what we're trying to show. The first thing we want to show is that the upper corner matrix has to be positive definite. And then we get C minus something is still positive definite. Okay, so the upper corner is easy. Let's let X not equal to 0 be otherwise arbitrary. What happens if we set then y equals 0? Well, okay, then we've got x, 0, looks like a 6. X, 0 transpose, A, B, B transpose C. Okay. Well, that's a 0. Okay, this vector is non-zero because we took x not equal to 0, and this matrix is positive definite, so this is strictly greater than 0. But now when we multiply this out, we get ax plus b times 0. Okay, we get b transpose x, 0 in the bottom, and then we get x and 0. So just multiply that out. X, 0, transpose. Here, I get a times x. Here, I get b transpose times x. And this is just equal to x transpose ax. Okay. This times this. This is transposed, and then this times this. Okay, so this says that A is positive definite because x transpose AX is bigger than 0 no matter what x is, because we had x arbitrary but non-zero. Okay, you see the strategy? We use the definition of positive definite, then we just make a special choice for x and y, and we pick off that component. That one's really easy. Questions on that? How do we get this other one, okay? Because if we just wanted to show C positive definite, we do the same trick, but we need C minus something. So that one's a little bit harder. So claim 2, C minus B transpose A inverse B is positive definite. Okay, so now we let y not equal to 0 be otherwise arbitrary. Hang in there. And we're now going to make a special choice of x. I'm going to have it solve ax plus b times y equals 0. Okay, how do you possibly come up with that? Well, you have xy here, and you notice if ax plus by gets me 0 here, that's got to simplify the calculation somehow, okay? It's got to. So I can do this because, oh, come on. A is invertible, y is arbitrary. So that just means x equals A inverse by, and can do okay, I already know A is positive definite, so A is invertible. Okay. Yeah, there's a minus sign here. Yep, thank you. I left the space for it, but I didn't write it, you know, blank. Thank you for catching that. You make everything easier when there's minus sign is in there. Okay? Now, y is not equal to 0, so because y is not equal to 0, x, y equals minus a inverse by. Can I dictate and have somebody come up here and just write? That would be so nice. Okay? This is not equal to the 0 vector, okay? Y is non-zero, so we don't care what x is that function of y, so that's non-zero. Now, m is positive definite, so we get 0 is less than x, y transpose, and we do a, b, b transpose c times x, y, okay? So ax plus by, I get 0 here, okay? So this is x, y transpose. I'm just going to figure that out. I get 0. And then I get b transpose x plus c times y. Okay, so then x transpose times 0 plus y transpose times this quantity is what I get. So I get y transpose b transpose x plus y transpose c times y. Now all I'm going to do is substitute in for x. So I have y transpose here, I have b transpose, and then x was minus a inverse b transpose times y plus c times y. And I'm almost there. So here's y transpose. Take the c out front, just doesn't change anything by the order. Well, I can't have b transpose in both places. There's no transpose here. Substitute in. X is a inverse by minus sign. Okay. Okay, so conclusion, C minus B transpose A inverse B is positive definite. Okay, so this middle matrix M here is positive definite. Take any x, y not equal to 0, I get something that's positive. And so I take y arbitrary and a very special x, and I work everything out, and I end up getting y transpose C minus B transpose A inverse B times y. Y is arbitrary, and this is positive, so this matrix is positive definite. Okay, so this would be if I was conditioning the measurements on the states. We typically use the other one, the one if and only if 3, but we're doing the one if and only if 2 today. Okay, so that shows we've now completed if M is positive definite, the upper left-hand corner of M, which is A, is positive definite, and then the Schur complement of A in M is also positive definite. Now we want to go the other way around. Just take those two facts and try to deduce that M is positive definite, and we'll be done. Yes, please.
So you only show this for the special x, y. You just come up with like, is this? So what we just did show that this is true for any x, y.
Okay, so yes, M is positive definite, okay? We're taking the fact that for any x and y not equal to 0, xy transpose M xy is positive. Now, from that condition, I want to deduce others. So now, just if it's true for all x and y, then it's true for special choices of x and y. And if by making those special choices, I can make a positive definite pop out, and then C minus B transpose A inverse B pop out, then I'm fine, because I'm taking the condition M positive definite and deducing what follows. Okay, so I think it was super clear on this one. I just take x not equal to 0, and then when y is 0, I see that x transpose AX is positive for all x is not equal to 0. So A is positive definite. Okay, when we go the other way around, I think it will get to the concern that you have. And then I take y arbitrary and a special x, and that's how I get the C minus B transpose A inverse B positive. So I just take special cases of this and I deduce other facts from that. And so back to your it's true for every x not equal to 0, this is positive, because x was arbitrary. And it's true for every y, this quantity is positive, because I let y be arbitrary and I choose a special x. You still look satisfied.
Yeah, but what if I don't choose that x?
Well, then you can deduce some other fact that B transpose A minus 14.7 times this, whatever, that quantity you might deduce as positive definite. It's not useful. Okay? Now, here's a weaker thing than the Schur Complement Theorem. If M is positive definite, then A and C each have to be positive definite, okay? How would I do that? I take my xy is x0, and then the next time I take 0y. So that's how I get that A and C are positive definite. But that's not, Schur's theorem is something much stronger, because it says C minus a positive definite quantity still remains positive. It's a stronger result. So I just take a different combination of x and y. So we can talk more after class if you want, if others have that. Okay, so let's go that B implies A. So we have A positive definite and C minus B transpose A inverse times B, that whole quantity positive definite, implies M equals A, B, B transpose C is positive definite. Okay, so I really think this will fix everything up, but let's see. Okay, so we want to take that the individual pieces have this positive definite quantity to get that the entire matrix is positive definite. So here's claim 3. If I take two vectors and sum them, If I do this, I just get V1 transpose M times V1 plus 2 V1 transpose M times V2 plus V2 transpose M V2. We've already done something like this before. I mean, recall if I do x plus y inner product with x plus y is inner product x with x plus 2 times inner product x with y plus inner product of y with y. So it's really the same thing. You're just using linearity on the left and linearity on the right when you multiply matrices and vectors, okay? Here's the abstract version of that. So V1 transpose MV1, 2 V1 transpose MV2, V2 transpose MV2. Okay, so that's an exercise for you guys. Proof is an exercise. Many of you have already done the proof in your head just sitting here. That's fine. Here's claim 4. Define x tilde equals x plus A inverse B times y. Then the vector x tilde y is not equal to the 0 vector if and only if the vector xy is not equal to the 0 vector. Okay, so I think this is what you wanted in the previous proof, but we didn't need it. And this one we do, okay? So I'm just going to take, here's my x and y, and I'm going to create a special other x, calling it x tilde. Remember, one of my hypotheses is that A is positive definite, hence its smallest eigenvalue is positive, hence it's invertible. So this all makes sense. So how do you prove this? Well, suppose y is not equal to 0 here. Then y is not equal to 0 over here, right? Okay, so proof. If y is not equal to 0, then the result is obvious. Okay, reviewers hate it when you write that, but we're still going to do it, okay? So now we look at the case. What if y is 0? If y is equal to 0, is it true that this quantity is not 0 if and only if this quantity is not 0? Well, how are these two quantities related when y is 0? They're the same, okay? So if y equals 0, then x tilde equals x, and the result is also obvious, okay? So, okay, remember we call these things proof by exhaustion. This one just wasn't very exhausting, okay? You just enumerate the cases and then you prove each one separately. Okay, so that's a little result. Okay, now. Claim 5. X, Y transpose times A B transpose C times xy equals x tilde transpose A x tilde plus y transpose times C minus B transpose A inverse B times y.
Professor, is the B transpose on the...
Oh, I'll keep writing it down, yeah. You guys know it's not there, so it's not there, okay? You guys know it's not there. It's not there. A, B, B transpose C. The other ones are correct, appreciate it. No, totally thankful. Okay, so why is this claim the final coup de grace, okay? What is the definition of positive definite? Well, as long as this vector is non-zero, this quantity needs to be positive. We just checked by the previous claim, this vector is non-zero if and only if x tilde and y is not the zero vector, okay? But this is positive definite, and this is positive definite. So, at least one of these terms is strictly positive, okay? This is positive definite. This is positive definite, okay? So we get that M is now positive definite. This is not equal to zero. The x tilde and y are not identically zero. At least one of them has a non-zero component. So either this is positive or this is positive. So this is what you want to do. Proof. Just multiply it out. Okay, and this is much too boring for a Rob 501 lecture. So just do it as an exercise. Okay, so once you have this, it's done, and so now you just got to multiply out these matrices. You guys are totally capable of checking left-hand side as right-hand side, and this proves the result. Okay, so done. Okay, and then when you're checking claim 5, go back and look at claim 3. It's very useful to do it, okay? Because here's a V1 and here's a V2. So you can go back and do that. But however you want to do it, just check left-hand side equals right-hand side. Okay, so let's do some examples. And we'll get the results that we heard about at the beginning of the lecture. Okay, so A, M equals A, B, B, C, 2 by 2, positive definite. Okay. So by Schur's complement theorem, this matrix, it is symmetric, right? No problem. It's positive definite if and only if A is positive definite, or positive, okay? And C minus B 1 over A times B is positive. getting there. Okay, so that's the same thing as A is positive, and once A is positive, whoops, I can multiply this equation by A, and the strictly greater than 0 stays true, and then this becomes A times C minus B squared. Okay? If and only if AC minus B squared is positive. And once again, I need A strictly greater than 0, or I mess up this strictly greater than sign. Okay, so that's Schur's complement theorem. So that's if and only if A is positive and determinant of M is positive. So if we put 3 minus 2 minus 2, 3. On the exam, you start calculating eigenvalues. Good luck. All of your classmates go 3 is positive, and then 9 minus 4 is positive, positive definite, okay? So don't be that one. Make it somebody else in the class who does the eigenvalues, okay? And then we just change it, and we'll keep all of the entries positive, you see? This is just to emphasize greater than 0 has nothing to do with the entries being positive or negative, okay? So here I'm making them all positive. And you go 2 is positive, 4 minus 9 is negative. This is not positive definite, right? Not positive definite. You like that? Yeah. This old guy sure had something pretty cool going, okay? So we just applied this result in the case of 2 by 2. This is just working with the slightly different choices of x and y. Okay, so that's one example. B, let's do M, and I'll make a particular choice. Okay, so if you're given this, it's up to you how you partition this. You might make this A, and then this is B and B transpose, and this is C. Or you could make this C, this becomes A, this becomes B, and then this becomes B transpose. It's your call, right? Schur is completely agnostic. You can check the upper corner, you can check the lower corner, and then you check the complement, okay? It's up to you, they're strictly equivalent. It's just that sometimes this is easier to check, and certainly sometimes one of these is easier to invert. That's the key part, okay? So that's all we got to do. Just got to make a choice here. Whoops. And the way I did it was like this. Okay, so A is 2, B is 1, 1, and C is 2, 1, 1, 3. It's no harder if you make the other choice. You can check that at home. So is M positive definite? Okay. We check A equals 2 positive, so that's done. And we check C minus B transpose A inverse B. So that's equal to 2, 1, 1, 3 minus 1, 1. A inverse is a half. 1, 1. One, 1, 3. And let's see, I worked this out. You get minus a half, and then 1, 1, 1, 1. Equals 3 halves, 1 half, 1 half, 5 halves. Three times 5 is 15, minus 1 is 14, positive definite, okay? Does your paper do that? Only mine. Check, okay? Conclusion, M positive definite. So that's what exam problems look exactly like that, okay? They look exactly like that. Question? No. Stretching? Yes. Yawning? Yes. Okay, so wrap up, and then we're going to do one more thing very quickly. Schur's complement theorem. We don't check the eigenvalues. We break it down into smaller parts. Once you have this matrix formed, you can apply Schur Complement's theorem again. Okay? And again and again. So algorithmically, it's not a problem. Where it will be important to us is this will be uncertainty in the measurement. This is uncertainty in a state we're trying to estimate. And when we take our best guess of the state given the measurements, we reduce the uncertainty by this amount. And so that's what's going to be super cool when we do Gaussian random vectors. Okay, conditioned. What's our best guess this? Conditioned on we've made these measurements, they have these values. How does that change our current estimate of what x is? And then we'll do that recursively even. Okay, so for the next part, I just want to go over quickly this handout that I posted. So you can read it. So let's suppose that our matrix M is positive definite. I just want to revisit the overdetermined system, A alpha equals B. I still assume that A has full rank. The columns of A are linearly independent. I'm still finding my alpha to minimize a norm, but this time my norm is coming from X transpose MX times a half. What this allows me to do is components of X where, I'm really looking at this as an error term. Where I have real certainty about my measurement, I'll make those weights big because those errors should be important because I'm very confident in those. And where I have a lot of uncertainty, I make the weight, those entries in M smaller so that errors there contribute much less to my norm, okay? That's why you do a weighted least squares. You put heavy weight where you're confident and low weight where you don't know very much, so mistakes there don't contribute to what you're doing. So I just want to resolve the regression problem when I don't have the identity matrix in here. So we solved it earlier, and you guys have used it in your homework when M is the identity. I think you're pretty good with that. So the solution is going to be, we use the projection theorem. Our vector space is Rn, our field is the reals. We define a new inner product as X transpose Mx, where M is positive definite. This is given to us for now, but in practice, you build it from your knowledge of and your confidence in the measurements you're making. As before, we break A up into its columns, and what we're really trying to solve is find the best X in the column span of A that approximates B. Because A times alpha is just a linear combinations of the columns of A. So we use the normal equations. The best X is a linear combination of the columns of A. And those coefficients satisfy the Gram matrix times alpha is equal to this coefficient beta. And we do the ij entry of the Gram matrix as the inner product of the columns of A, but now there's a weight. That's the only difference. So instead of being the identity here, we have a weight. And so that's the ij entry of the matrix A transpose MA. So this is the new Gram matrix. It's not A transpose identity A transpose weight times A. The other part of the normal equations, as you look at the right-hand side of this equation, the ith entry is B, inner product with the ith basis vector. So that inner product is B transpose MAI instead of identity. It's a scalar, so I can swap it, but M is symmetric. And so that's the ith entry of the matrix A transpose M times B. So that's where the weight shows up here, and the weight shows up here. So these are the normal equations. We know the columns of A are linearly independent, hence this matrix is invertible. It's a Gram matrix. It's automatic. We don't have to check anything. And hence, there's the best weighted estimate of your coefficients. Okay. So it's just using the normal equations and computing the Gram matrix with the new thing. That's it. Ta-da. Okay, lecture's done. Anybody else? I've only had 2 people come by and ask about the moving window and the derivative estimate. Is everybody finding that to work, or there's questions? Does anybody have any worth talking about it? If you have a question?
Does the estimate depend upon the value of M? So in my code, for some values of M, the estimate just doesn't make any sense. For some values, it does.
What do you mean by M, the length of the window? Okay, so let's see what we're doing. If you don't want to stay for this, this is not lecture, okay? It's just homework. So we're trying to estimate this function, right? So, and we have data points. Whoops. what I'm having you do is calculate the slope. So there's the naive derivative is just rise over run. This point minus this point divided by the distance, and it's a constant sampling rate. So that one will work on the first problem, and then on the other problem where these things are kind of a blur, it just gives you brrrr, which is what you see on so many robots, okay? Okay? So, when you have noise, you would like to average the slope. How do you average? You regress. You do an overdetermined equation. So what's a simple solution? Take 3 points and fit a line through it. You could take 5 points and fit a quadratic through it and then differentiate the quadratic, okay? Now, some of you were trying to take the entire curve and fit one function to it and then just differentiate that. That doesn't work. Why? I'm a robot. I've got an arm, and my master wants to do a PD controller on one of my joints, okay? I've got encoders. Those encoders have, say, a step of, say, let's just say it's 0.1 degrees, and I'm sampling every millisecond. So if I'm moving kind of slowly, look what's happening. Because of the step, I'm getting constant, 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 constant step, constant, 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 2 steps, constant, constant, okay? Now look what my derivative is looking like if I do the naive. 0, 0, 0, 0. 0.1 degree divided by a millisecond is now moving at 10 degrees per second. 0, 0, 0 is now 20 degrees per second, back to 0, 0 minus, okay? Stupid, okay? Stupid. First of all, in real time, I cannot look to the future. So I can only use my current measurements, okay? Now, I could keep this vector getting bigger and bigger and bigger, but suppose I am operating for an hour and I'm sampling at a millisecond. How big is that vector going to get? Really big. And guess what? How correlated do you think my derivative at this point is to what happened an hour ago on my arm? There's no relationship, right? So why would I keep all that data? So that's what the moving window is. I take my last M measurements. M is, say, 5. Okay? 1, 2, 3, 4, 5. That's the moving window. Question, next question I've been asking people in office hours. Here's the derivative, here's the derivative, here's the derivative, here's the derivative. Now we're thinking this is the origin because I put an axis here. If I move my axis to here, how did the derivatives change? They don't. What if I move it here the next point? How does the derivative change? It doesn't. So, what can I do? Each point in time, I can say that's t equals 0. It doesn't matter. Okay? So this is now minus delta t, minus 2 delta t, minus 3 delta t. And these have the same values even when I now get 2 more data points and I move my axis to here. So suppose I'm writing y equals a0 plus a1 times t. And I'm going to do 4 points because I'm lazy. Okay? So my y vector has 4 points. That's fine. What does my A matrix look like? 1, 1, 1, 1, right? For my measurement at t equals 0, I've got 0 here. For my measurement here, I have delta t, minus 2 delta t, minus 3 delta t. Okay. My alpha is a0, a1. what does y dot equal to at t equals 0? It's just A1, right? Second component of alpha. So here's the thing, okay? You can just try doing this, a slope. You can change this from 4 to 3 to 7 to whatever. It's very easy with a for loop. But this matrix does not change each time I add a data point, because I just call that 0. It's just all relative, okay? And so my regression is alpha hat equals A transpose A inverse A times Y. Y changes each time my data comes in. This matrix does not. So you calculate it once. Do not calculate it every millisecond, okay? It's stupid. It's constant. You just put it at the top of your file. This is now just a matrix that you then multiply the vectors by, and then you just pick off, if you're doing a line, you pick off the second component. Now, questions? How would it have changed if you called this point 0 and then this was 3 delta t? Okay, I flip these, and then when I calculate y dot, I'd be calculating y dot at 3 delta t. So then it's A0, excuse me, it's A1 times 3 delta t. That is still a constant as well, okay? So there's no problem, I just got to get that formula, but then I need to calculate the A1. And I just multiply it by 3 delta t, 4 delta t. So I don't care where you put 0, but just move it so that your A matrix stays constant. And then differentiation is just multiplication by a matrix times the vector. But that is exactly what the naive derivative is when it's y at tk